All right, thank you very much. My name is Jim Freericks. I'm going to tell you about calculations that model pump probe experiments on electron-phonon coupled materials out to picosecond timescales. And one of the applications of this is I'm going to show you how you can create a perfect conductor by somehow it's cut off here on the screen. Okay. By driving the phonon into the unstable maximum of a double well potential. All right, so pump probe experiments. This is a situation where you have a pump that is an intense electromagnetic field followed by a delay time, and then you have a probe that comes afterwards. And you can vary the delay time with the different probes to study how the dynamics evolve over time. If you're looking at something like a photoemission spectra, the photoemission spectra is constructed from the lesser Green's function, and then it looks like a Fourier transform, but it is weighted by these probe envelope functions. And you need to have these probe envelope functions to get a positive photoemission spectra, which is a requirement for the experimental and theoretical results. I'm going to now tell you about this in charge density waves. We're working in one dimension. We're looking first at a Holstein model. Holstein models have static phonons in them, and we're first looking at the limit where the mass is infinite. We will then later look at adding Ehrenfest dynamics into that with non-zero masses. Even in one dimension, there's no finite temperature phase transition, but as you lower the temperature, you can see that you start off at high temperature with something that looks like a pseudogap that deepens, and then eventually when you get to zero temperature, you do have something that forms into a nice charge density wave looking density of states. So how do we run this algorithm? Well, the first thing we do is we start from the equilibrium phonon distribution at the initial temperature. We then sample the phonon configurations on the lattice using that distribution. We're going to be using, in the language of the first talk that we had today, multiple Ehrenfest trajectories that we'll be averaging over as opposed to a single Ehrenfest trajectory. We'll diagonalize the electron problem for each of those configurations to determine the time evolution for each step. We then compute the Ehrenfest forces and then evolve the phonons. And then we repeat this. And we also then construct the measurable quantities and evaluate them. And I'd like to say, for those of you that are familiar with things like ab initio molecular dynamics, this is a very similar process to what you would be doing in an ab initio molecular dynamics type calculation, except we are looking at electronic properties. Usually in molecular dynamics, you're focused on the ionic properties. So at t equals 0, the initial phonon distribution is two delta functions. This is coming from the semi-classical nature. This is actually an artifact of the problem that isn't so great because it's not what you would get in a quantum mechanical system. As you increase the temperature, those two delta functions broaden into Gaussians and start overlapping. And then when you get to very high temperature, if this will work. If you get to very high temperature, it then becomes a single peak Gaussian. So in the result that I'm going to be talking about, we're going to be coupling directly to the electrons, not to the phonons, and using short femtosecond pulses. And the way that the phonons are excited then is through the electron-phonon interaction, and they'll act as if they're being impulsed by this force. So the model here is going to be good for initial temperatures that are on the order of the phonon frequency or higher because of this problem that the system has. If the temperature is too low, it's not going to look like a quantum mechanical system. It also cannot describe superconductivity. It can only describe charge density wave order. So the motivation for this work comes from an experiment that was done by New Gedik's group, and it's a very interesting experiment. In this charge density wave phase, you have a double well structure, and what they looked at was as you excite and change the fluence of the excitation, they were able to excite the system into what looked like putting it in this unstable or metastable point where you're at the top of the effective middle of this double well potential. And they saw that by looking at a relaxation time that grew to be very long and then fell off again as they changed the fluence and increased the fluence. In our theoretical calculation, you can see here this scale, it's not short. This is on the order of, the time scale is on the order of, 500 femtoseconds. So this is a long kind of a time scale for relaxation. When we do our calculations in this Holstein model, starting at t equals 0, we can actually, find this range extending out to even as long as, 4 picoseconds. So we can find this interesting metastable range. Our tuning is much more sharp than what was required in the experiment. If you look at this scale, we're only going over a 10% change in the electric field, whereas this is changing this fluence over a much more substantial region. So we're finding a much more sharper peak for this region in the numerical calculations that we're doing. So let me illustrate this for you with some movies that show the evolution. This is the phonon, photo emission, and it starts off having a gap, but after we pump, you're going to see the gap is going to shrink in size due to the energy that's been added in the system. This is the phonon, the average phonon coordinate. You're going to see it's going to be oscillating back and forth in a single well because we're hitting this with a low fluence. So as you can see here, you see this slow shrinking of the gap, but it never gets to 0. And as this oscillates back and forth, you can see that the gap region is going to oscillate back and forth. This is the so-called amplitude mode oscillation that you typically see in a photo emission. If we now go to, I can get this to go. If we now go to the strong coupling, strong electric field, strong driving, what you're going to see is the gap is going to close. Again, if I can get this, whoops, I got to go back. Okay, try again. Okay, so now what you can see in strong driving, this average phonon coordinate blows right past what was the original maximum in the center. You also see that it actually is a well-defined minimum, and this is occurring because of the way in which the electron-phonon coupling, you can see this change in the slope here. That is what is affecting it. You actually have something that is a somewhat stable local minimum that this can sit in. If you look at the photo emission itself, what you see is the gap is completely closing, and in fact there's a reversal of the order parameter as this average phonon coordinate goes onto the opposite side of the spectrum, and then the gap will open again when it's far to the left or far to the right. Now, what is interesting is when we get into this critical region, what you're going to see here is a slow dynamics that is driving up to that maximum, and you're going to see this gap close and sort of sit stably there as the system is being driven up to this maximum. And there are fluctuations. These are looking at what is happening at individual sites in the system. You can see that this is actually jiggling back and forth a little bit, but it stays in this point and stays in this region for a fairly long period of time. So what can we do with this? What is interesting and happening here? One of the things that's interesting, so we're plotting a number of things here. We're plotting order parameter. We're looking at some of the derivatives of that order parameter, but the one I want you to really focus on is the current here. What you can see is when you're driving it close to this decoupled state, this current can last for a really long period of time. This is 4 picoseconds that the current is lasting in. As we saw again in the first talk, typically an electronic current is going to decay on the order of a few femtoseconds. So this is really interesting metastable system that is sustaining current over a long period of time. That's what you would expect in something that's a perfect conductor. Why is it a perfect conductor? Well, when I drive the phonon coordinate to 0, the electron-phonon coupling is G, coupling strength, times X, the average phonon coordinate, times the electron density. If X is equal to 0, the electron-phonon coupling is going to vanish. So you can see that in this plot where we're looking at the energies. We did these studies both for Holstein and SSH model. Here in this critical region, the electron-phonon coupling is the orange line, and you can see it's driven to 0 in this transient region. There's no electron-phonon coupling energy because we dynamically drove the electron-phonon coupling to 0. And one of the things I want to end with is showing you that this really is a perfect conductor. So what we did here was we started it off, drove it to that metastable point where the phonon coordinate is 0, and then we added a small DC field, really tiny DC field. If it's very small, what we find is we get a nice current that again lasts here on the order of a picosecond or so. If we drive it a little bit harder, we actually see damped block oscillations being driven in the system. And so again, it's not a perfect conductor because of the metastability, but it displays a lot of interesting behavior that you would have in a perfect conductor, which could be useful for things like switches that are ultra fast but then turn off over a short period of time that you can tune by determining how you set up this particular metastable state. Okay, and with that, I just want to thank the people who did this work. Marko Petrovic was a postdoc at Georgetown when he did this work, and Manuel Weber is in MPI Dresden, and this is work that was supported by the Department of Energy and by NERSC. And I'm happy to answer any questions if you have them.
I'm just one quick question. So I know the system, I kind of lost which kind of system. I'm interested in looking at phonon decouplings. I'm going to talk to you after the session as well because I have interest of time. But what kind of system, how big is the system we are modeling with?
So these kinds of calculations we can run on system sizes. We were typically running on sizes that are on the order of 30 lattice sites up to about 100 lattice sites on a 1D system. So they're somewhat sizable systems, but as you know with these things, the calculations are long and hard. And it takes a lot, so we're always somewhat limited on exactly what we can see. So you could see the fact that we had finite size of the system in that photo emission spectra because it had the little peaks in it, as opposed to being a nice smooth curve.
Thank you so much. I'll definitely go up my deals section, but a fantastic talk. Thank you once again, speaker, and thank you.